Students, welcome back. We are now going to talk about the words endothermic and exothermic. Endothermic is a reaction or a process where energy is absorbed. We would say energy is one of the reactants, which is, of course, one of the chemicals on the left side of the arrow. So, for example, when bonds break, energy has to be absorbed in order for the bonds to break. Bonds don't just break on their own. You have to put energy into the bonds to break them. So that putting energy into is endothermic. I always think into endothermic. Energy goes into the reaction for it to be an endothermic reaction. So the energy is absorbed. So breaking bonds between atoms requires energy. Again, it can't just happen on its own. So energy has to go into the bond to break it. So it's endothermic. This also includes breaking up intermolecular forces between molecules as well, which we'll talk about more. Now, exothermic is when heat exits or comes out, it's released. So the energy or the heat is on the product side, which is the right side of the arrow in a chemical reaction. So when bonds are made, energy is released. So imagine two atoms. They're very unhappy, right? Atoms are mostly unhappy. They come together and make a bond. That makes them very happy, which lowers their energy. So that energy has to go somewhere. So it gets released, it exits. Exiting energy is exothermic. Exit, exo. So making bonds between atoms releases energy and is an exothermic process. This also includes creating intermolecular forces between molecules. When we create attractions, again, that lowers the energy. The energy has to go somewhere, so it exits. So endothermic, heat goes into the reaction. Exothermic, heat exits the reaction. All right. So, thinking about the system and the surroundings, the system is the chemical reaction itself. That is the black box, A plus B makes C. Okay, that is the chemical reaction. The surroundings would be the thermometer and the beaker. Okay, I know it says flask, but it's a beaker. Okay, so the surroundings surround the chemical reaction. So again, endothermic, heat goes into the reaction. So heat is absorbed by the reaction, which is the system, and it's transferred from the surroundings to the system. So heat is going from the surroundings into the system, which is the chemical reaction. Now, exothermic is the opposite. Heat is released by the reaction. It exits the reaction, which is the system. So heat is transferred from the reaction, which is the system, to the surroundings. So the surroundings heat up. So let's think about how these things will feel to us if we're holding that beaker. If we're holding the beaker and it's endothermic, heat is transferred from the surroundings, our hand, to the reaction. So heat is leaving our hand and it's going into the reaction. That makes us feel cold. Now, exothermic, if we're holding that beaker, heat is exiting. So it's coming out of the reaction to the beaker. So the beaker is going to feel hot to us. So exothermic feels hot, endothermic feels cold. All right, heat of reaction and delta H. Delta is that triangle and it means change. So let's learn what that means, delta H. The energy of a chemical reaction depends on how much energy is required to break all the bonds between the reactants versus how much energy is released when the new bonds, the new atoms bond together to make the products. So it's kind of a toss-up. It depends. So this change is called delta H. It's the heat of the reaction or enthalpy. Enthalpy is what H means. So it's basically the heat of the products minus the heat of the reactants. Final minus initial. So the heat of reaction delta H can be called change in enthalpy, as I mentioned. The H in delta H is the symbol for the word enthalpy. The units are typically in kilojoules because the change in energy for a reaction is pretty big. So remember, kilo means 1,000 times larger. So there's 1,000 joules in 1 kilojoule, right? There's 1,000 joules in 1 kilojoule, just like there's 1,000 meters in 1 kilometer, a kilometer. All right. So we're going to look at reaction profiles. And this is something very important in this chapter. Okay, the first law of thermodynamics is important. Understanding exo and endothermic is important. And energy profiles are important. Reaction profiles. So reaction profiles are going to have some things in common. And I'll show you the picture of the profile in a minute. But we're going to have a line where the reactants start. That's their energy or heat. We're going to have a line where the products are located. That is their energy or heat. Now, to connect those two lines together, we're going to have a hill, a curved mountain in between them. The height of that hill is the activation energy, E sub A. The activation energy is the minimum amount of energy required to go from reactants to products. So we have to get over that energy mountain. The top of that energy mountain is the transition state, TS. That is a very unstable chemical where the bonds are half broken and the new product bonds are half formed. So this is very high energy and unstable, the transition state. It's like the halfway point in between the reaction. So the reactant molecules are breaking apart and the products are being formed. So you can't stop there, right? You can't bottle that. It's very unstable. And then the difference between products and reactants is delta H, what we just learned, the heat of reaction or the change in enthalpy. Okay, so we're going to draw reaction profiles. So we start with an X and Y axis. Then we need to draw our lines where the reactants start and where the products are. And these vary on who is higher up depending on whether it's exo or endothermic. So you always include a title for a graph. The y-axis is going to be heat or energy. Same thing. Heat is a form of energy. So heat or energy. The x-axis is the reaction pathway or progress of reaction. You'll see both on these graphs. So if we start over to the left, that's 100% reactants. And as we go across the x-axis, we're turning from reactants to products until we're 100% product. All right, here is the reaction profile for endothermic. So let's look at our axis. Again, our y-axis is heat. Our x-axis is the reaction pathway or progress of the reaction. The blue line on the left shows you where the reactants are starting. Okay, where the reactants are starting, and they're down pretty low for endothermic. Then we have the blue line, the reaction pathway going up to the transition state, which is the highest point. Then it comes down to the products. Okay, the products are higher than the reactants because it's endothermic. Endothermic means heat goes into the reaction. So we have our reactants and we have to raise up to the products because that heat is going up. Okay, so the products are higher because we absorbed heat energy. So the products have to be higher than the reactants because we absorbed heat energy. Look at the reaction above. We have reactants plus heat make products. Okay, so reactants plus heat. Heat is a reactant. So this is endothermic. Okay, the delta H value is positive because the heat energy went up. So it's a positive value. Delta H is positive. Again, reactants go up to products. We have the transition state at the very top. The E sub A is the activation energy. It's the height of that mountain from the reactant level to the transition state. That energy height is the minimum energy needed to go to the products. So we have to get over that energy hill. And then delta H is the difference between reactants and products. That is delta H on our graph. Okay, so hopefully you understand that graph for endothermic. Let's look at exothermic. This time, the reactants start up high. The reactants are higher than the products. Okay, so the reactants are on the left there. That blue line is the reactant heat energy level. We have to go up to the transition state, then we go down to the products. And the products are lower than the reactants. That's because this is exothermic. The heat exited, it went to the surroundings. So we started out with reactants, but the heat exits, so the heat goes down to the products. So the products are lower. The transition state is still the top of the energy hill, right? That's where the reaction is halfway done. So it's high energy, intermediate process up there, that transition state. The activation energy is still in pink. It is the height of the hill from the reactants to the top of the transition state. Okay, activation energy is always reactants to the top of the transition state. And then delta H, the change in enthalpy, again, is between reactants up high and products down low. That difference is delta H, and it's negative because it went down. We went down to the products. So it's a negative energy. Look at that equation over there on the side. Reactants go to products plus heat. See, heat exited the reaction. It's produced. It's on the product side. Reactants go to products plus heat. So this is an exothermic reaction. The products are lower than the reactants. Delta H is a negative value. All right, I hope that makes sense. See you in the next video. Goodbye, GCC.